Okay, so let's get started and take a look at each one of these questions. Again, if you have a question, just type it in the chat. So let's see here. Yeah, let me start with this. There we go. So, gotta write your name. Okay, so let's start with, oops, that's not the right thing. That was the actual exam. So I will close that. And I will stop recording. Stop. Here it is. No, that's not it either. K102. Hold on, I sent myself the wrong file. Let me try to find it here. Here we go. Here's the right file. Sorry about that. Just give me 2 shakes of a lamb's tail. We'll get set up here. There we go. Okay. Now I'll open up my Teams, start broadcast. Okay. Share. Can you all see this? Can you see the review now? Yes. Okay, good. Thanks, Tyler. Thank you, Kamish. Good. Okay, thanks, Jasmine. Okay, now we're really ready to get started. Okay, so it says here, what is another acceptable name for this compound, 4-chlorophenol? So the first thing I would do is start by drawing phenol. And so phenol is when we have a benzene ring with a hydroxyl, right? That's one of the common roots of benzene I asked you to memorize. So phenol. So if I have a 4-chlorophenol, so it's going to look like this. So I'm going to have my phenol. And remember, this carbon counts as carbon 1, 2, 3. And then at the 4th carbon, I'm going to have a chlorine. So another name, it says here meta 4-chlorophenol. Well, you remember that meta, when we have something that's meta substituted, that's like a 1,3 substitution, and we need a 1,4. It says here in B, para-chlorophenol. That seems a little bit more reasonable, right? Because para means 1,4 substitution. So if we have something like this, if we have X and Y, and so the answer would be para-chlorophenol because the chlorine is para to the hydroxyl in the phenol. All right, let's take a look at question number 2. Which of the following statements about the compound is false? So you see that we have this alcohol here. Okay, so we have here's the longest carbon chain. Let's see, there's the longest carbon chain. It's an alcohol. Anyhow, let's take a look at the first one. It says it is a tertiary alcohol. I would say this is not a tertiary alcohol because the carbonyl-carbon is attached to 1, 2 carbons, so it can't be that. The next one, it says its name is 2-methyl-3-pentanol. Is that the answer? Is it looking for what's false? Oh, good gravy. I hate questions where the answer is the first one. So the answer must be A, okay? So that's the one that's false. Can anybody tell me what type of alcohol this is if it's not a tertiary alcohol? Sorry, let me bring it up here, Tyler. Yeah, it's a secondary alcohol, absolutely. So it's not a tertiary alcohol. It is a secondary alcohol. The other ones are all true. Its name is 2-methyl-3-pentanol. It can participate in hydrogen bonding because it has an OH group, right? If you have a hydroxyl. It can be oxidized to form a ketone. The answer to that is yes. So if I have 1, 2, 3, 4. So if I draw the bond line structure, of course, I can oxidize a secondary alcohol to a ketone like this. That's something we can do. And it contains both a polar and a nonpolar region. Yeah, I'd say so because this part, right, this is definitely polar. A hydroxyl is polar. But all of these hydrocarbon parts here, these are nonpolar. And so the answer to this one is A. It is a tertiary alcohol is false. It's a secondary alcohol. Okay, let's take a look at the next one. It says, which of the following is not a possible alkene product from the dehydration reaction of 2-butanol? So first, let's start by drawing 2-butanol. So 1, 2, 3, 4. right? Because we have butane, okay, and on the carbon number 2, we're going to put our alcohol. Well, this is talking about dehydration, so losing water. And the way that we do that is by treating it with a catalytic amount of acid and by heating that. And what we're going to do is we're going to look at the carbon-all-carbon, and then we go to the carbons next door. So if I draw out the condensed structure, so CH3, CHOH, methylene, and then another methyl group, right? This is dehydration, right? Loss of water. So we're going to lose the part of the water is going to come from the hydroxyl, right? But where does the other hydrogen come from? Well, remember, I told you that you look at the carbon-all-carbon, okay? And then you go next door. There's 2 carbons next door, and they are not identical to each other. So if I look at the CH3, if I remove one of those protons, okay, I would end up forming a double bond here between the methyl and the carbon-all-carbon. So that would give me this compound, right? That would give me this molecule, which is 1-butene. The other possibility, I'll highlight it in yellow, is if I was to take one of these hydrogens, okay, then I would end up with this molecule, okay, which is 2-butene. Okay, now you see that 1-butene is in A, so that's a possible product. 2-butene is here. Now, if you look at C, can anybody tell me what the major problem with C is? There's a big bad problem with C that should just, like, red lights should go off immediately. What's the big, huge, mega problem with C? Okay, so I'm not getting any answers for that. Okay, well, how many carbons are there in 2-butanol? There are 4 carbons. How many carbons are there in C? 1, 2, 3, 4, 5. That's impossible. You grew a carbon? No, that's impossible. So that must be the answer. That's impossible. You cannot make that molecule. You can't create matter. Now, the reason that D is a possibility is because this molecule is actually cis-2-butene, but when the dehydration occurs, you can form the cis, or sorry, did I write cis when I meant trans? You can form both the trans 2-butene, and you can also form the cis 2-butene. Okay, and the reason why is because there's free rotation about this bond. All right, so the answer is C. And even if you didn't know how to draw the Zaitsev product or the Hoffman product, you could still figure that out because you can't create matter. Is everybody still there? Are my students still there? Just double checking. Yes, okay, good. All right. Well, let's move on to question number 4. It says, what type of alcohol does not undergo oxidation under normal conditions? Who could tell me? Which one is it? The answer is tertiary, right? Because we can take a primary alcohol and a secondary alcohol. So if we take a primary alcohol, we can oxidize that to an aldehyde, and it can either be further oxidized to give you a carboxylic acid. A secondary alcohol can be oxidized to give you a ketone. So that will oxidize to give you a ketone. And a tertiary alcohol will give you no reaction. Okay, nothing will happen when you try to oxidize a tertiary alcohol. Okay, let's take a look at this one. This is just a nomenclature problem. So the first thing that we do is we identify the longest carbon chain that contains our hydroxyl. And we want to give the hydroxyl, the OH, we want to give it the lowest possible number. So we would start numbering from the right in this case. So we would give it 1, 2, 3, 4, 5, 6. So it's some kind of 2-hexanol. So you see we have a 2-hexanol here. And the methyl is on the third carbon. So I should say A, B, C. Anyhow, so the answer is 3-methyl-2-hexanol. 3-methyl-2-hexanol. Okay, let's move on. If you have any questions, just stop me. Which of the following alcohols is a tertiary alcohol? This is a good one. You just have to draw them all. So let me help you with the A, B, C again. So 1-butanol is 1, 2, 3, 4 carbons, and then we have our hydroxyl. So this is primary. 2-butanol, you probably already know, which is this, is a secondary alcohol. 2-methyl-1-butanol would be 1, 2, 3, 4. 1-butanol, and then we have a 1,2-methyl. That's a primary. D is 2-methyl-2-butanol. So 1, 2, 3, 4. If we have 2-methyl-2-butanol, this is a tertiary alcohol. So this one must be the correct answer. And then we could just do the last one for fun. 3,3-dimethyl-2-butanol. So 1, 2, 3, 4, 2. And then on here we have this. So this is also a secondary alcohol. So the answer is 2-methyl-2-butanol is a tertiary alcohol. D. All right, let's move on and talk about which of the following statements concerning glycerol is false. Glycerol is one of those alcohols that I talked about in the videos. You had to know the structure of glycerol, which is 1, 2, 3 carbons. It's 1, 2, 3 trihydroxypropane. The reason glycerol is so important is because glycerol is the product of the hydrolysis of fats, of triglycerides. Oops, there we go. It says here, glycerol contains 3 hydroxyl groups. That's true. Glycerol is a viscous liquid. Yes, glycerol is viscous, and the reason why is because there's so much hydrogen bonding going on with all of these hydroxyls. It says here, glycerol is sweet. That is true. That was one of the facts that I told you in the slide presentation. Glycerol is a diol. What's the problem with glycerol as a diol? Who can tell me how I would correct that statement? Glycerol is a... Exactly. Glycerol is not a diol. It's a triol, okay, because it has 1, 2, 3 hydroxyl groups. And glycerol is definitely formed from the hydrolysis of fats. Okay, number 8. An unknown compound is highly water soluble. That's the first fact we're given, right? If it's highly water soluble, we know some things about water solubility. Okay, so it's highly water soluble. Forms a silver mirror in the Tollens test. What do you know about a compound if it forms a silver mirror in the Tollens test? Who can tell me what that means when I get a silver mirror in the Tollens test? Can anybody tell me why that would happen? Why would you, when you take a compound and you react it with the Tollens test or the Tollens reagent and you get that beautiful silver mirror, why is it? Is it because it's a hydrocarbon? No. Is it because it's an aldehyde is present? That is correct. It's because it is an aldehyde. So we know our mystery compound is an aldehyde. It also says it forms a red precipitate in the Benedict's test. Can anybody tell me what that would mean? If you react a compound with the Benedict's reagent or Benedict's test and you get a red precipitate, what does that mean? An aldehyde is also present, correct. So it's a double whammy. So we know it's an aldehyde, okay? So you look at A is a ketone, so it can't be A. You look at B is a carboxylic acid. Carboxylic acid, so it can't be that. C is an aldehyde, okay. And what else? D is an ester, so it can't be that. But E is also an aldehyde. Ooh, this is interesting. So now it comes down to a war between C and E. Can anybody tell me what I would be able to do to differentiate between these two? How do I know which one to choose? Lower number of carbons. Okay, that's true. And what does the lower number of carbons mean, Tyler? You're right that this is, you're both right. This is the correct answer. And the reason why is because it's highly water soluble, right? This is going to be water soluble because it has less than 4 carbons. C has 1, 2, 3, 4, 5, 6 carbons, right? The longer the chain, the less soluble it is, okay, in water, okay? So the longer the chain, okay, the less water soluble it will be. All right, so the smaller aldehyde is going to be more water soluble. Number 9, what type of compound is produced in a reaction between a ketone and 2 alcohol molecules in a trace of acid? This is a tricky one for students, okay? So this is one where you had to pay really close attention in my videos. So let's go through it, okay? And I will ask a question about this on the exam. So if I take a ketone, like acetone, let's say, okay, so this is a ketone, okay, it's acetone. If I treat it with 2 alcohol molecules in the presence of a trace of acid, so let's pick an alcohol like cyclopentanol, okay? So if I take this and treat it with cyclopentanol, so here's my ketone, my alcohol, and I treat it with a catalytic amount of acid, who can tell me what the first compound I'm going to form will be? What kind of compound is it? What functional group will be found? And it's a new functional group, kind of new. It's not an enol, no. So what you're going to form is a hemiacetal. Okay, so this is very important. I will ask a question about this. Okay, so the way I explained it in my videos is that oxygen is more electronegative than carbon. Carbon is electropositive. So what happens is you form a bond between a lone pair on the oxygen and this carbon. Okay, but carbon cannot have 5 bonds, and so you break the pi bond and you move the electrons up here like this. So what you end up with is you have the 3 carbons from your ketone. You still have the oxygen attached, right? This oxygen right here. But then you have the oxygen from the alcohol attached. So let's draw the rest of the alcohol. Okay, and where did the hydrogen from the alcohol go? It goes on the other oxygen, okay? It goes onto this oxygen that I'm highlighting in yellow, okay? And that group, or that functional group that we just formed, is called a hemiacetal. Okay, so what the hemiacetal does is it's going to react with another molecule of alcohol, so a second molecule of our cyclopentanol, okay, in a trace amount of acid, all right? And what we're going to end up forming is an acetal in this case. Okay, so what we do when we form the acetal is we replace the entire hydroxyl, we replace it with all of this part of the alcohol. Okay, so that's what we're going to do. So we're going to start with the 3 carbons. Oops. We're going to start with the 3 carbons from our original ketone. We didn't touch this part at all. That's going to stay the same. Okay. Now we're going to have all of this part of this molecule attached. Okay, so let's draw that in. We have another piece from our other alcohol. And what's left over? Well, you're going to be left with H2O. Okay, so we have to write that as a product as well. And so let's scribble that in. This is our acetal. Okay, and then we have to write plus H2O to balance the equation. Okay, so you have to be able to recognize a hemiacetal and an acetal. So if you look at a carbon, if you have a carbon, okay, if you put an alcohol on it, a hydroxyl, and an ether on it, like that, okay, and we just fill in the rest with our groups, that is the generic formula for a hemiacetal. Okay, and if you look at this hemiacetal up here, here's the carbon, okay, here's the hydroxyl, and here's the ether portion. Okay, so it still works. An acetal is you have a carbon with 2 ether groups attached to it, and the 2 R groups attached, and this is an acetal. Okay, so here's our carbon, here's one ether group, here's the other ether group. Okay, so hemiacetal and acetal. You have to be able to draw this because I sent the exam to the printer just the other day, and I will ask a question about acetals and hemiacetals. Let's take a look at this interesting ketone here. It's a cyclic ketone. It says, which of the statements below is false? I don't know why I'm so hung up on false questions or false statements. It says here the name is cyclopentanone. That's definitely true. It's a cyclic ketone that has 5 carbons in the ring, so cyclopentanone. Yes, that's correct. The molecular formula is C5H8O. That seems reasonable, right? Reasonable, because all of these are methylene, CH2, 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 and then I have a carbon here, so that's 5 carbons, a total of 2 times 4 hydrogens and 1 oxygen, so that seems reasonable. And I'll delete all that. There we go. Molecules of this compound are held together by dipole-dipole attractions. Absolutely they are, right? If I have a dipole in my molecule, which I do because oxygen is more electronegative than carbon, okay, then I do have a dipole, and 2 molecules of cyclopentanone will be held together by a collection of dipole-dipole interactions. Can be formed from the oxidation of cyclopentanol. So D, let's see, if I take cyclopentanol, which we looked at in the previous question, it is a secondary alcohol. And if we talked about this earlier tonight, if I oxidize a secondary alcohol, I get a ketone. So that seems reasonable. And it says here, it can be oxidized to produce a carboxylic acid. You cannot make a carboxylic acid from the oxidation of a secondary alcohol. It's impossible. So this would be the correct answer. That is the false statement. Okay, speaking of carboxylic acids, it says, what alcohol undergoes oxidation to produce acetic acid? Let's start by drawing acetic acid. Acetic acid has, can anybody tell me how many carbon atoms are found in acetic acid? How many carbons are there in acetic acid? Not a trick question because you had to memorize formic, acetic, propionic, butyric, valeric. How many? That's exactly right. There are 2 carbons in acetic acid. Now, you could write out the bond line formula, okay, which is this. I'm going to write out the condensed formula just in case. So here's acetic acid. This is acetic acid. And what's an alcohol that has 2 carbons in it? Who can tell me what alcohol has 2 carbons? Also not a trick question. There's only one alcohol with 2 carbons in it. Ethanol. Absolutely. So if I take ethanol, right? Ethanol is a primary alcohol. Ethanol. And I can oxidize ethanol to this molecule. And that molecule is called acetaldehyde. And I can further oxidize that ketone to give me acetic acid. So that's it. So really all you need to know is what's an alcohol with 2 carbons, and there's only one possibility, and it's ethanol. So we oxidize ethanol to give us acetaldehyde. Then we oxidize acetaldehyde even further to give us acetic acid. So the answer is ethanol. All right. Let's see here. What is the Iupac name of the compound shown? Well, there's one. Oops. There are 1, 2, 3 carbon atoms in the molecule. So this must be, who could help me? I'm sure somebody knows. Yeah, it's propanol. Absolutely. So the answer is propanol. Could anybody tell me the common name of this molecule? It'll take you longer to type it out. So what's the common name of this? Okay, this is the kind of thing you need to know. It's propionaldehyde. All right, so you have to know the common names of formaldehyde, acetaldehyde, propionaldehyde, butyraldehyde, and valoraldehyde. All right, which of the following will give a silver mirror when treated with the tolerance test? And we agreed earlier on that if you have a silver mirror with the tolerance test, okay, that means that you have an aldehyde. Okay, so pentanone is a ketone. Propanone is also a ketone. Hexanal is an aldehyde, right? So these two are ketones. Hexanal is an aldehyde, so it is the correct answer. And 1 pentanol is an alcohol, and 2 pentanol is an alcohol. So there you go. That wasn't too bad. Okay, it says here cyclopentanone reacts with one molecule to give you what? A hemiacetal. I told you earlier on that a hemiacetal is like when you have an R group, a carbon, sorry, with a hydroxyl and an ether on it, okay, and your 2 R groups. That's a hemiacetal. Which of the following correctly represents the structure of the hemiacetal? So look, if we draw our ketone, cyclopentanone, okay, and we draw our alcohol, which is ethanol. Remember, I told you there's a dipole here, like that. So that means that this carbon is partially negative and this carbon is partially positive. The electrons from the ethanol are going to be attracted to the partially positive carbon, and you're going to end up breaking the pi bond. And when you do that, you end up with this. So let's draw what we've got. We still have our oxygen here, and we still have the alkoxy group. So the only question becomes, where does this hydrogen go? And the answer is, it goes on to the other oxygen. And this is our hemiacetal. This one is not a hemiacetal. The second one is the correct answer. B is the hemiacetal. So that looks good. The next one is not a hemiacetal. It's only got 1 oxygen, right? A hemiacetal has 2 oxygen, so that's impossible. So it cannot be C. It can't be D because this is just an ether. Okay, it's not a hemiacetal. And this, I don't even know what the hell that is, so that can be in no way correct. All right, let's keep moving. It says here that 1-heptanol has a pleasant aroma and is sometimes used in cosmetics to enhance fragrance. Draw the condensed formula of 1-heptanol. Is it primary, secondary, or tertiary? Well, hopefully by now you got this one down. We could start by drawing the bond line structure. If it's heptanol, that means it's got 7 carbons. So look, when my pen touches the paper, that's carbon 1, 2, 3, 4, 5, 6, 7. And I'll put a hydroxyl at carbon number 1, like this. Okay? What the heck happened there? Anyhow, I'll put a hydroxyl at carbon number 1, right? Because I have 1, 2, 3, 4, 5, 6, 7. So this is 1-heptanol. Okay? Could anybody tell me, is this primary, secondary, or tertiary? Not a trick question. Mr. Deon isn't. Yeah, exactly. It's a primary alcohol, right? Because if you look at the carbonyl-carbon, it's only attached to 1 other carbon, right? If you still need to draw complete Lewis structures, I don't feel like doing this, but for the sake of instruction, right? If you need to draw in every stinking hydrogen, if that helps, you can do that. It's very time-consuming, but if it helps you get the question right, I'm all for it. So this is the complete structural formula of 1-heptanol. And again, you can see that the carbonyl-carbon only has 1 bond to another carbon, making it a primary alcohol. Okay. Let's keep moving. Question number 16. It says, give the Iupac name of this giant molecule. Let's draw it out carefully. We have a methyl group. Then we have a methyne, a CH, okay? And attached to that, in brackets, we have this hydroxyl. So we'll draw it off like that. Then we have another methyne, or CH. Then we have another hydroxyl attached to it. So I'll put it here, like that. Let's see here. Then we have a methylene, a CH2. Then we have a CH3. So this is a diol because it has two hydroxyl groups, right? 1, 2. We want to number it such that we give those hydroxyls the lowest possible number. So we're going to do 1, 2, 3, 4, 5. And the longest carbon chain has 5 carbons, so it must be a pentane diol. And the way you would name this is you prefix pentane diol with the numbers, with the numbers of the locants, excuse me, or the numbers of the two hydroxyl groups. So this would be 2, 3 pentane diol, 2, 3 pentane diol. Okay, good. Let's take a look at the next one. It says, show how acetone, so acetone is the same thing as propanone. So we could write that in. So this is acetone, okay, or propanone. Show how acetone can be prepared from propene. And propene would be this molecule here. This is propene, or propylene. Anyhow, propene is all you need to know. Write the corresponding chemical equation using condensed or line structures. I don't know if I would ask this exact question, but I get the point behind it. Okay, so you take propene. Okay, if you were to treat this with a catalytic amount of acid and water, you would get a Markovnikov addition, right? You would get Markovnikov addition, right? The rich get richer. This carbon has 1 hydrogen. This carbon has 2 hydrogens. And so when you do that Markovnikov addition, you would end up with this alcohol, which is 2-propanol. So 2-propanol. And then if I want to convert that into the ketone, I would oxidize that, and I would end up with propanone. And so the way, if you were in the lab and somebody said, I want you to make acetone or propanone from propene, first you would treat it with water and a catalytic amount of acid. Then you would treat it with an oxidizing agent. It might be chromic acid. It might be potassium permanganate and base. And then you would make propanone or acetone, same thing. Okay. All right, there we go. So that's how you would make acetone from propanone. Acetone comes from the petroleum industry, so you don't have to worry about doing that reaction in real life. But anyhow, it says here, give a common name for this ether. So I talked about how to come up with common names for ethers, and I said you can make the common name by looking at the two alkyl groups, and you can look at them in terms of alphabetical order or size. But in this case, there's only one possible name because on this side, on this side, we have an ethyl group, okay? And on this side, we have a propyl group. Just to refresh your memory, an ether is an R group and then another R group like that. That's an ether. Okay, so we have an ethyl and we have a propyl. And so we would call this ethyl propyl ether. That would be the common name for that molecule, ethyl propyl ether, because it follows the alphabetical rule in that you put alphabetical order, E comes before P in the alphabet, and it also follows the size rule, which is we list the smaller alkyl group first. So either way, this would be ethyl propyl ether. I put this question in here deliberately because I wanted to at least look at one example before the exam where you have a hydroxyl as a substituent. Okay, so remember, this molecule, like somebody asked me a question about this a while ago in the class. This molecule, okay, this is phenol. Okay, if I have this molecule, this is cyclohexanol. Okay, and if I have this molecule, maybe I should move this up a little bit. That's cyclohexanone. If you have an alcohol and a ketone in the same molecule, the ketone will be the king of the castle. So we're going to name this molecule as a cyclohexanone. And whenever I have an OH group, a hydroxyl, I call the substituent a hydroxy. So I would call this carbon 1, 2, 3. And so this would be 3-hydroxy cyclohexanone. 3-hydroxycyclohexanone. So again, the take-home message here is if you have an alcohol and a ketone in the same molecule, the ketone takes on the suffix, and the alcohol becomes a hydroxy, okay? So when it's a substituent, we call it a hydroxy. Something that we don't look at very much in this class are what are known as bifunctional compounds. Those are compounds that have more than one functional group in the same compound. As you can imagine, they get very tricky to name. But this is one specific case where we do look at a bifunctional compound, or a compound with two functional groups, two different functional groups. Okay, let's take a look at this one. It says, which of the following is the condensed formula for a generic carboxylic acid? Who can answer this one for me? Which one would be a carboxylic acid? A, B, C, D, or E? Yeah, Kayla's got it. Everybody's got it. It's D. Yeah. So this is a carboxylic acid. I didn't mean to use that color. Anyhow, that's the carboxylic acid. If you look at the other ones, so this is nothing. It's not any functional group. There's no such thing as RCOH, right? Because the carbon doesn't have 4 bonds, so that's impossible. This is also nothing. This is just a pile of crap. Okay, I have no idea what that is. This would be an ester. Okay, and we're not looking for an ester. And this is also nothing. This is also garbage. That is not a correct condensed anything. Okay, so the answer is D. Let's take a look at this question. It talks about ethanoic acid. Can anybody tell me what the common name of ethanoic acid is? There's a common name for this, and we looked at it earlier. Oh, I guess it's one of the answers too. Since ethanoic acid would be a carboxylic acid with 2 carbons in it, right? This is ethanoic acid or acetic acid. Right, ethanoic acid, that's Iupac, International Union of Pure and Applied Chemistry, and acetic acid is the common name. Okay, so it contains a carboxyl group. That seems reasonable because a carboxyl group is this, the carboxylic acid group. So that's correct. Its condensed formula is CH3CH2COOH. What do you think of that? Does that seem reasonable? Yes or no? Does B seem reasonable? Too many. I like the way you think. Too many carbons, right? Let's write it in the way you said it. Too many carbons. Okay, this is propanoic acid or propionic acid. Okay, and so the statement that's false is this one. Okay, the common name is acetic acid. Oops. The common name is acetic acid. It has 2 carbons, not carbons, and it is a very polar compound. Carboxylic acids generally, so carboxyl groups are very polar. All right, let's move on from there. It says if we take a carboxylic acid plus an alcohol and we treat it with a catalytic amount of acid or acid and heat, we lose water. And what else do we form? Who can tell me what functional group is formed? I'll draw a carboxylic acid. Who could tell me what functional group we form? This is one of the most important reactions you will learn in this class. On the old ACS final, it came up in like 4 questions. Yes, you form an ester, right? You form an ester, so you would end up forming R. What's left over? I showed you. You lose water, which comes from everything I've highlighted in yellow. You end up with R, your carbonyl, and then a bond to an oxygen and the other R group. So you form an ester. Okay, this reaction is known as esterification. Very important. It's one of the most important reactions we look at. Okay, so we end up forming an ester when we react a carboxylic acid and an alcohol in acid. Okay, number 23 says, what two compounds will react with hexalacetate when heated together in the presence of a trace of acid? Okay, well, this is also a question about an esterification reaction, because it says we're taking two compounds and we're producing hexalacetate, which is, oops, what's going on? Hexalacetate is an ester. Son of a gun. Hexalacetate is an ester. So you should be able to draw the structure of hexalacetate. And I went over this in my videos. The acetate comes from the carboxyl portion, and this portion, the hexyl, comes from the alcohol portion. So if I want to draw hexalacetate, right, acetate comes from this part, acetic acid, and hexyl comes from hexanol. So we have 1, 2, 3, 4, 5, 6. Okay, so how would I form that compound? It says a trace of acid. Okay, what are the two compounds? I would need acetic acid and hexanol. 1, 2, 3, 4, 5, 6. So I would need acetic acid and hexanol. Did anybody notice there's one thing missing from my balanced equation? Who can tell me what's missing from my balanced equation? What am I missing from this balanced equation? Plus what? What did I lose? Is anybody there? Yes. Okay. Yes, it's water. Okay. Oops. H2O. All right. In esterification, this is another example of esterification. One of the most important reactions. Okay. We take an carboxylic acid plus an alcohol, and we produce an ester and water. Okay, let's move on from there. It says draw an example of the hydrolysis of an ester by aqueous base and provide the name of the reaction. So not only when we form an ester, so formation of an ester is called esterification. Okay, and that is when we take an acid, a carboxylic acid, plus an alcohol. This is the third time I've gone over this, okay, tonight, and a catalytic amount of acid, and we produce an ester plus water. Okay, so let's write that out again. Carboxylic acid, alcohol. Okay, we produce an ester and water, but this is a reversible reaction. Okay, you can also hydrolyze an ester. That means to break apart. So now that you've made an ester, you need to learn how to break it apart. So if I take an ester, okay, and I treat that with aqueous base, so hydroxide, sodium hydroxide, potassium hydroxide, it doesn't matter. But when I take that and I treat it with aqueous, so water, and let's say something like sodium hydroxide, or let's just write OH minus, and then I heat that up, now I can blow it apart. There are two carbon-oxygen bonds in an ester. There's a carbon-oxygen double bond and a carbon-oxygen single bond. Which one of those is going to be weaker? Well, the answer is the single bond is the weaker one. So that is the bond we're going to break. We're going to break this bond right here, okay? So then what are we going to be left over with? We're going to have this part of our acid, and then we're going to have this part from our alcohol. So how do we finish these up? We're going to take the ester and we're going to form a carboxylic acid and an alcohol. So from my water molecule, okay, I need a hydroxyl and I need a hydrogen. Okay, so I form a carboxylic acid plus an alcohol. Okay, and can anybody tell me what the name of this SATSI reaction is? It's got a really cool name. Who could tell me the name of this reaction? Hydrolysis of an ester in base. Saponification, that is correct. Okay, so the hydrolysis of an ester in aqueous base is called saponification. Okay, because it's the way the pioneers used to make soap. Speaking of soap, it says here soap molecules form when my cells are formed in water or dissolved in water. What part of the soap molecule is oriented inside? So you should have looked at my video about my cells, and you have the polar carboxylate head on the outside like this, okay? And then you have the hydrocarbon tails on the inside like that. And on the picture in our book, it's really gross. It looks like a piece of earwax or something on the inside, okay? It's got something like this, you know. Okay, it looks all gross. So this is the dirt. So who can tell me which part of this, my cell, is going to be oriented on the inside of, Okay, remember, this is in water. So which part would be on the inside? Okay, if the water is out here. Son of a gun. The hydrophobic portion, exactly. So the answer is the hydrophobic carbon tail. The hydrocarbon tail, right? These are all the tails, okay? This is the hydrophobic carbon tail, because dirt and oil and grease are largely nonpolar, okay? This part up here, this is the polar carboxylate head. And I'll point out that it's also negative, right? Because a carboxylate, okay, a carboxylate is this. It's the conjugate base of a carboxylic acid. Okay, well, with that in mind, let's move on. It says, draw an example of a reaction between an acid chloride and a carboxylate anion. Name the functional group that's formed. So this is another reaction I went over in the carboxylic acid chapter. If you take an acid chloride, which looks like a carboxylic acid, but you replace the OH with a chlorine atom, so this is an acid chloride. If I take that and I treat it with a carboxylate, I'm going to draw it like this, just for instructional purposes. Let me fix up that lone pair, which is kind of ugly. There we go. Here's our carboxylate. Okay, carboxylate. What's going to happen when I react those two together? Okay, the negative charge, right, from my carboxylate is going to be attracted to the delta plus on this carbon, right? Because carbon-oxygen is a polar bond. We see that every day in organic chemistry, multiple times a day. So what happens is you form a bond between the oxygen and the carbon. And what happens is it hits the carbon so hard that you actually lose the chlorine atom. You probably saw the picture that I had included in my slide of acetyl chloride reacting with water. I had there was a beaker of water, and somebody was using a dropper or a pipette, and they were dropping in acetyl chloride in here, and it made all kinds of like smoke and fumes or something. So when that happens, let's look. What are we going to have? We're going to have our R with our carbonyl, Then we lost the chlorine. Okay, that's gone. And then we have a bond to what? To this oxygen. Okay, and what's that oxygen bound to? That's bound to another carbonyl like this. And then I have R prime like that. Who could name this functional group? A new and exciting functional group. Brand new and exciting functional group that's covered in the Carboxylic Acids chapter. It's an anhydride. That is correct, right? Because you lose what? You lost water. Or it looks like you lost water. Anyhow, I shouldn't have put that in there. I should have put plus chloride. Okay, so this is called an anhydride. And where does the name anhydride come from? I explained that in my slides. But basically, if you took 2 carboxylic acids and you heat the snot out of them, which is not a great thing to do, but if you do it, you will lose H2O and you will form an anhydride. Not a great way to make an anhydride. It's actually kind of dangerous, but it works. Okay, so that's where the word anhydride comes from. Anhydride means loss of H2O. Okay, let's move on. The next one, it says, which statement best explains why propanoic acid boils at a much higher temperature than hexane? So if we draw propanoic acid, propanoic acid, that's a carboxylic acid with 3 carbons. So that's this carboxylic acid, which is the same thing as drawing the bond line structure like this. And if I draw, what's the other molecule? Hexane. Hexane is this, CH3, and then I could put all my methylenes like this, okay? Or I could draw the bond line structure, 1, 2, 3, 4, 5, 6, okay? Either one is fine. Who could tell me which one of these is the best answer, A, B, C, D, or E? Yeah, C, absolutely. C is correct. It says propanoic acid molecules can hydrogen bond with other propanoic acid molecules, but hexane is nonpolar and cannot hydrogen bond, right? This is related to IMFs, intermolecular forces. Okay, so you have to know your IMFs. Hydrogen bonding is strong. Okay, and what are the forces associated with the intermolecular forces, associated with hexane molecules? Could anybody tell me? It's not one of the questions on here. London forces, exactly. Yeah, so we could put that in here. London forces only, whereas propanoic acid has H bonding. Okay. All right, let's try another one. It says here, come up with an Iupac name for the following compound. It's not very big, is it? Could redraw it like this, CH3, CH, methylene. So right away, you can see it's some derivative of butanoic acid, because we see that our longest carbon chain has 4 carbons in it. And then we have a chlorine on carbon number 1, 2, 3. So this must be 3-chloro-butanoic acid. That would be the Iupac name. If we wanted to write down the common name, remember we used the alpha, oops, that doesn't look right. Use the alpha, beta, gamma, and then delta, so on and so forth. So it would be beta-chloro-butyric acid. Okay, it doesn't ask for it, but it's always fun to try those. Number 29, what is the Iupac name for the missing product from the following reaction? Look, we're taking an ester, we're treating it with water and acid. This is a hydrolysis reaction. right? Hydrolysis of an ester. Hydrolysis of an ester can be done in acid and it can be done in base. When it's done in base, it's got this funky name, which is saponification. Okay, so whoever was handing out cool names for reactions, when they came to acid hydrolysis of an ester, they didn't care. Okay, so they didn't give it any special name. It's just called hydrolysis of an ester and acid. And that's what is going on here. So which bond are we going to break? We've got a carbon-oxygen double bond and a carbon-oxygen single bond. Single bonds are weaker than double bonds, so we're going to break this bond. So let's write down what we would have left over. We would have our carboxylic acid portion, which is over here, and the other portion is going to be an alcohol, right, which is going to come from this part. So we're going to have our alcohol, and then we have 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons, and this is 1 butanol, and that's the acid hydrolysis. So, you know, one time I was working in the pharmaceutical industry. Did I tell you? I think I might have told you this story that we interviewed somebody. I might have put it in my videos where we interviewed a student and we said, you know, this is their job interview. Okay, this is after 1 semester of organic chemistry. So I'll put the interview in this box. We said to the student, can you draw benzoic acid? She said, yes. So she drew this. She said, here is benzoic acid. And then we said, could you draw the methyl ester of benzoic acid? So she said, yes, I can. Okay. And she drew this. This is methyl benzoate. And we said, yes, that's absolutely correct. Then we said, could you draw the product of the hydrolysis of the ester of methyl benzoate? And she said, do you want me to do it in acid or base? And we said, you got the job. Okay. Because she knew right away that if I hydrolyze it in acid, okay, versus I hydrolyze it in base, I get 2 different scenarios. If I do it in acid, I end up with benzoic acid, okay, plus methanol. If I do it in base, I end up with the benzoate, okay, plus methanol. So when you do hydrolysis in base, you end up with an anion, the carboxylate. You don't end up with an acid, right? But when you're in acid, you get an acid. Makes sense? Okay? Anyhow, that's just kind of an aside. So with that in mind, let's look at question number 30. It says, draw a reaction between butanoic acid and potassium hydroxide. I'll do it in green pen. So if I take butanoic acid, so 1, 2, 3, 4. So this is butanoic acid. Remember, in a carboxylic acid, this is the acidic proton. That's the acidic hydrogen atom. So when I react that with potassium hydroxide is a strong base, right? This is a strong, super strong base. You can burn yourself with this really, really badly. And what's going to happen is the hydroxide is going to rip off that proton to form what? You should remember this from general chemistry or chemistry 1. The reaction between an acid and a base produces a salt plus water. So one of the products is going to be water, right? And that's going to come from H2O, okay? And then the other product that you form is the carboxylate. So let's draw the carboxylate, which would be this, okay, right? Which is this. And then our cation is going to be potassium. And the way I would name that is I would call this potassium butanoate. Okay, so that is the final answer, is you end up with potassium butanoate. All right, that's the name of the product. Okay, I think we only have a couple more questions here. Question 31 says, what 2 compounds will react to produce methyl hexanoate in an acid catalyzed esterification reaction? We looked at a question almost identical to this earlier on. So the first thing is you have to be able to draw methyl hexanoate. So the hexanoate that comes from the carboxylic acid of hexanoic acid, and the methyl, that comes from the carboxylic acid portion. So if I draw methyl hexanoate, 1, 2, 3, 4, 5, 6 for my hexanoate, and then a methyl group. So this is methyl hexanoate. And then it says if I do the acid catalyzed hydrolysis, okay, or no, sorry, it's not talking about hydrolysis. It's talking about how would you make this compound? What two compounds? So I would have to take hexanoic acid. So 1, 2, 3, 4, 5, 6. I'd need this carboxylic acid and methanol, right? And I would form methyl hexanoate and I would lose water. So the answer is hexanoic acid and methanol. Okay, question number 32 says dehydration of a primary alcohol produces a mixture of alkenes. The best way to solve this one is to look at a specific example. Let's say we had 1 butene, okay? Sorry, we're talking about primary alcohols. Let's say we had 1 butanol, just for example. It works with any alkene, or alcohol, sorry, any primary alcohol, because this is a primary alcohol, sorry. Okay, so we look at the carbonyl carbon. It only has one next door neighbor. Okay, so there's only one possible product. You would remove H2O. So you take off one of those hydrogens in the hydroxyl, and you would end up with, in this case, 1 butene. Okay, there's only one possible product, so you will not get a mixture. No mixture possible. Okay, so the answer is false. All righty, let's keep moving. And it says here that oxidation may be classified as the gain of bonds to oxygen and the loss of bonds to hydrogen. That is true. That's one of the ways that we define oxidation in organic chemistry, is that this is 100% true, right? Reduction is gaining bonds to hydrogen and losing bonds to oxygen. Okay, the next one says, oops. The next one says stepwise oxidation of a primary alcohol first produces an ether and then a carboxylic acid. We looked at this earlier. We said if we take an alcohol, so this is a primary alcohol, ethanol. Okay, and this is just an example. Okay, we first oxidize that to an aldehyde, and then we oxidize it to a carboxylic acid. So this statement is false, okay? False. You do not produce an ether first. First, you produce an aldehyde. And again, this is a reaction we've looked at several times this evening. Number 35, liquid diethyl ether contains an extensive network of hydrogen bonds. Who could tell me if this is true or false? Is this true or false? Number 35. False. Thank you, Kayla. Absolutely, right? If I have 2 molecules of diethyl ether, okay, there are no hydrogen-oxygen bonds, okay? Bonds present. So the answer is false. That cannot happen. Number 36, it says the formation of the disulfide bond between two sulfhydryl groups, is an oxidation process. So if we look at the sulfhydryl group, so if I take 2 sulfhydryl groups and I react them and I form a disulfide, is this oxidation or reduction? Or can somebody just tell me if this is true or false? Is this true or false? The answer is this is true. True. Because we're losing hydrogen, right? We're losing bonds to hydrogen. Both of these are gone. Okay, when we take, this is a sulfhydryl, okay, and this is a disulfide. Okay, this is how perms are done. If you've ever had a perm before, they basically take the disulfide bonds in your hair, oxidize them, and then they wrap your hair around a curler, and then they reduce it to reform the disulfide bonds, and it makes the little curls. Anyhow, Benedict's test can be used to distinguish between an aldehyde or a ketone. Is that true or false? True. That's right. So an aldehyde with Pope Benedict's test, okay, gives you a red precipitate. If you treat a ketone with the Benedict's test, you get no reaction. Nothing interesting happens whatsoever. The next one says a ketone will react with a Tollens reagent, but an aldehyde will not. We'll just call this one pretty quickly. This is false. Okay, only an aldehyde will give a silver mirror. And the last one, oh man, how many questions did I put on here? A hemiacetal contains 2 Ethern functional groups. Can anybody tell me if this is true or false? We looked at the hemiacetal a couple of times tonight. Yeah, this is false, okay? The hemiacetal, okay, so whether we're making an acetal or a hemiacetal, we always start with the 2 R groups. A hemiacetal has a hydroxyl and an ether. An acetal has 2 ethers, okay? So this is false. False. It should say an acetal contains 2 ether functional groups, right? One here and one here, okay? Ether and ether. This is a alcohol and an ether. Okay, the compound shown below is the enol form of butanal. I'll help you out with this one. That is false. So if I draw butanal, which is this compound, butanal, okay, the enol, the double bond is going to be formed between the carbon of the carbonyl group and the carbon next door. So it would look like this. So there's my 4 carbons. So the double bond would be here, like that. And then my alcohol would be like that. Okay? So this is false. Right? An enol, okay, an enol has to have this. You have to have a double bond with an alcohol attached to it. Okay? And I don't see that in here. You have the double bond, but the alcohol is far away from it. Okay? Saponification is the hydrogenation of an ester under basic conditions. Who could fix that statement? It's false. Who could repair this statement for me? Saponification is the what of an ester under basic conditions? Hydrolysis, exactly. It's the hydrolysis. Okay, it's when we take an ester, okay, and we treat it with a strong base, and we heat it up, and we form a carboxylate, okay, and an alcohol. Okay, number 42, the carboxyl group is found in all fatty acids. Would that be true or false? Well, if it's a fatty acid, right, it must be true, because a fatty acid is like this. It's like having a long tail on the end of a carboxyl group, like that. So this is true, right? Think about it. It's an acid, so acids contain a carboxyl group. The next one says traces of acid can catalyze both the formation of an ester and its hydrolysis. That is true, right? We looked at examples of both of those. We talked about the hydrolysis of an ester in acid, and we talked about the formation of an ester in acid. Okay, so look at esterification. So that's the formation, and acid hydrolysis of an ester. That's the hydrolysis. So make sure you look at both of those, which we looked at several times tonight. The oxidation of formaldehyde produces acetic acid. So let's start by drawing formaldehyde. Formaldehyde. So you should know formaldehyde, acetaldehyde, propionaldehyde, butyraldehyde, and valeraldehyde. If I oxidize this carboxylic acid, I get this acid. Could anybody name this carboxylic acid that I have drawn here? Can anybody give this carboxylic acid a name, the common name? I'll even take the Iupac name. A 1-carbon carboxylic acid, the simplest carboxylic acid there could possibly be. What would the name of that carboxylic acid be? Formic acid, that is correct. Formic acid. Now that, again, is the common name, and the Iupac name would be methanoic acid, right? That's Iupac. Okay, a single carboxylic acid molecule may contain more than one carboxyl functional group. Well, that's true. We looked at all kinds of examples. We looked at oh my stars, go away. We looked at oxalic acid, malonic acid, succinic acid, glutaric acid, adipic acid, so on and so forth. Okay, so if I look at just the structure of oxalic acid, it's the simplest 2-carbon carboxylic acid. So this is oxalic acid shown here. And you should look at the other ones too. So, oops, didn't mean to do that. Succinic acid, glutaric acid, and adipic acid. Okay, so oxalic acid has, so we'll put here number of carbons. Oxalic acid has 2, 3, 4, 5, and 6. Okay, and that's found in a table that's in our book.